Now you may be thinking, bravo, you clever scientists, for coming up with a new way to demonstrate that you are the last ones to recognize what common sense already told us is patently obvious. As the psychologist and author Gay Bradshaw declared, this is not news, it's Science 101. But it also speaks to the challenge of accepting a phenomenon that is fundamentally private, and to the historical reluctance of science to fully embrace it in anything other than a human. Fishes show the hallmarks of pain both physiologically and behaviorally. They possess the specialized nerve fibers that mammals and birds use to detect noxious stimuli. They can learn to avoid electric shocks and anglers' hooks. They are cognitively impaired when subjected to nasty insults to their bodies, and this impairment can be reversed if they are provided with pain relief. Does this close the book on the debate over pain and consciousness in fishes? Not likely. There may always be those who use the crutch of uncertainty to assert that fishes are pain-free. Even if the evidence for the few fish species studied is accepted as true pain, one can still claim that we just don't know for the myriad other fish species fortunate not to have been subjected to scalpels, syringes, or small foil heaters. No tan lie scientific consensus beyond consciousness and pain in fishes. Consciousness probably evolved first in fishes. Why? Because fishes were the first vertebrates, because they had been evolving for well over 100 million years before the ancestors of today's mammals and birds set foot on land, and because those ancestors would have greatly benefited from having some modicum of wherewithal by the time they started colonizing such dramatically new terrain. Also, it is likely that fishes' ancestors evolved consciousness because fishes today have abilities that are consistent with their being conscious and sentient. As we will discover, fishes use their brains to achieve some quite useful outcomes. From stress to joy. The fish's face is one of its notoriously weak features. Even allowing for the fact that it was the first real face ever attempted, little more can be said for it than that the mouth, nose, eyes, and forehead, if such it can be called, are in the proper order. It is of no use for frowning or smiling. If the fish could do these things, it would receive a great deal more sympathy than it does. Brian Curtis, The Life Story of the Fish. A woman shared with me a tale of two fishes. In late 2009, she bought a 5-gallon tank and 3 small goldfishes, an oranda, a blackmore, and a Ryukyu fantail. Like many novice aquarists, Lori knew little about how to care for fishes, and she purchased and lost several goldfishes over the ensuing months. But the original fantail and blackmore continued to survive. Lori named the fantail Seabiscuit and her husband named the blackmore Blackie. Lori came home for lunch one day and found, to her horror, Blackie trapped inside a decorative pagoda she had placed in the tank as extra stimulation for her fishes. Struggling to get out, Blackie was bumping repeatedly against the walls and windows of his plastic prison. He looked weak. Meanwhile, Seabiscuit was darting frantically at Blackie in what Lori took to be an effort to free him from the pagoda. Seabiscuit repeatedly charged at Blackie as though trying to budge him loose. Gingerly, Lori reached for the pagoda, and as gently as possible managed to work Blackie loose with her fingers. He was in poor shape. He had rubbed off all the scales and velvety finish on one side, and his right eye was swollen and raw. He hung listlessly at the bottom of the tank, barely moving. Lori didn't think he would survive. For the next few days, Seabiscuit stayed protectively by Blackie's side, and the little blackmore recovered. His eye healed, and a new set of scales gradually grew back on his damaged side. From that point on, Lori noticed a distinct change in the relationship between Blackie and Seabiscuit, and in her own view of them. Prior to the pagoda incident, Seabiscuit had been bossy, often chasing Blackie aggressively, but this behavior stopped. I began to perceive fishes as individuals with feelings and personalities. She moved them into a 20-gallon tank with a big filter and minimal furnishings. Blackie died in June 2015, age 6, apparently due to a faulty filter. Seabiscuit is hanging in there, with a newer goldfish companion named Too Much, who was rescued from a school carnival. A separate account, published in a South African newspaper 25 years earlier, has uncanny parallels to Lori's. It involved a severely deformed blackmore goldfish named, you guessed it, Blackie, who could barely swim. When Blackie was transferred into a tank containing a larger oranda goldfish named Big Red took an immediate interest in his disabled tank mate. He also began to provide assistance by placing himself just beneath Blackie. Together they would swim around the tank as a tandem, Big Red providing the propulsion that aided Blackie's mobility and access to food. After it was sprinkled on the surface, the pet store owner attributed Big Red's behavior to compassion. Emotional hardware. Stories like Laurie's and the South African pet store owners don't carry much scientific weight because they are isolated, anecdotal observations, and behaviors, and the emotions that underlie them are notoriously difficult to interpret. For instance, how are we to know that Seabiscuit wasn't attacking Blackie in the pagoda out of fear or stress? For me, the lasting change in the two fishes' relationship afterward is the more telling observation. It suggests that Blackie's mishap was a significant event and that it brought them closer. Putting anecdotes aside, what does the science say about fish emotions? A good place to start is the hardware in fishes' brains and bodies. Emotions involve relatively old brain circuits conserved through evolution and shared by all vertebrates. As we saw in the previous section, you don't need a big brain with a neocortex to feel petrified or pissed off. A growing cadre of experts believes emotions originated alongside consciousness. Reacting is sometimes better than thinking. Imagine you are an early marine creature suddenly confronted by a predator. If you have to think to yourself, "Gee, I better get out of here," you will soon be someone's meal. It is more useful to immediately flee in terror and leave the thinking for later. Emotions are closely linked to hormones, compounds produced by our glands that affect physiology and behavior. How the brain produces hormonal patterns, the so-called neuroendocrine response, is known to be virtually identical in bony fishes and in mammals. The inference is that these patterns might play out similarly in the conscious, emotional realm, that is, the psychoneuroendocrinology of these two groups might also be similar. Oxytocin provides an example of these parallels. Also known as the love drug, oxytocin is associated with bonding, orgasm, labor contractions, nursing, and the feeling of falling in love. Researchers from McMaster University in Hamilton, Canada, have discovered that the fish version of this same hormone, oxytocin, also regulates behavior in different social settings. When adult male daffodil cichlids were injected with either oxytocin or a saline solution, the saline-treated controls showed no discernible behavioral changes. In contrast, oxytocin-treated fishes became more emotional. They were more aggressive toward a larger perceived rival when placed in a simulated competition over territory. Surprisingly, mid-ranking cichlids injected with oxytocin showed submissive behavior toward other members of their shoal. The authors speculate that the submissive response ensures these highly social fishes, which are cooperative child rearers, remain a cohesive, more stable group. It may not be love, but it is a nice and friendly response. Another way to investigate fish emotions is to look for parallels with mammals and birds by subjecting their brains to similar insults and comparing the results. One target of such comparisons is the amygdala, a pair of almond-shaped structures making up part of the brain's ancient limbic system. In mammals, the amygdala helps drive emotional reactions, memory, and decision-making. The medial pallium of a fish's brain appears to perform the role of the amygdala. When this region is either disabled or electrically stimulated, changes in aggression occur that mirror those seen in land-dwelling animals subjected to analogous treatment. Studies on goldfishes have also shown that the medial pallium is involved in an emotional response to a fearful stimulus. How do fishes show fear? For instance, how do they react when attacked by a predator? They respond as we might expect them to if they are feeling afraid. In addition to breathing faster and releasing alarm pheromones, they show classical behaviors shown by land animals when scared. They may flee, freeze, try to look bigger, or change color. For some time afterward they also stop feeding and avoid the area where the attack occurred. Might a fish become more relaxed when exposed to drugs that have an anxiety-melting effect on us? Oxazepam is one such drug, used extensively by human patients for the treatment of anxiety and insomnia, and for the control of alcohol withdrawal symptoms. When researchers led by Jonathan Clamander at Umeå University in Sweden caught wild Eurasian perches and exposed them to oxazepam, the fishes were more active and showed better chances of survival. Increased activity might seem a surprising response to a drug that relaxes people, but the fish's response is actually consistent with a relaxing effect. Tranquil fishes are less afraid to explore their surroundings. In this state, the treated fishes spent less time clustered with their allies and more time foraging, which might also explain their improved survival rate in a captive setting free of predators. Being relaxed is all well and good if you're in a safe environment, but fear evolved for good reason. It motivates us to flee and hide from danger. Fishes are capable social learners, readily learning to fear something simply by observing the reactions of others of their kind. For example, naive fathead minnows who were initially unafraid of unfamiliar predators swimming on the other side of a glass barrier soon learn to avoid those predators by watching the fearful reactions of experienced minnows. Fathead minnows also learn to avoid predators when exposed to Schreckstoff from other fathead minnows. Do they treat these odor-based clues to lurking danger as seriously as they do visual clues? Apparently not. Scientists from the University of Saskatchewan trained fishes that an unfamiliar odor was safe because it never led to negative consequences. In fact, the odor was from pike, a dangerous predator of minnows, but the minnows used in this study were collected from a pond where pikes do not occur, and so were presumed ignorant of pike odor and its implications. A group of control minnows received the same training regimen, only with blank water. On testing day, minnows from both training groups were exposed individually to pike odor paired with either fathead minnow Schreckstoff or a knowledgeable and therefore frightened model fathead minnow responding to the risky pike odor. Minnows who had no prior exposure to pike odor responded equivalently to the alarm pheromone or the fright reaction of a model minnow. However, minnows taught to believe that pike odor was safe showed little response to the alarm pheromone, whereas they showed characteristic fear behavior in response to their fellow fearful fathead. So, for a fathead minnow, at least, the sight of fear is more persuasive than the smell of fear. The study also supports the idea that, when it comes to predation risk, minnows trust other minnows more than themselves. It is better to heed a threat that turns out to be benign than to ignore a threat that turns out to be real. Or, as the old saying goes, better safe than sorry. Stress relief. Being able to remove oneself from fearful situations is not only important to survival, it favors long-term health. It is well known from unsettling studies of rats, dogs, monkeys, and other species, and indeed, from human victims of war and other prolonged hardships, that unrelieved stress can lead to all sorts of problems, including anxiety, depression, and lowered immunity. One of our body's responses to stress is to release cortisol. This so-called stress hormone acts to regulate stress, and it performs this function in other vertebrates, including fishes. A team of scientists from the Max Planck Institute of Neurobiology and the University of California studied genetically manipulated zebrafishes with a cortisol deficit. These fishes suffered from consistently high levels of stress, and they showed signs of depression in behavioral tests. When normal zebrafishes are placed in new surroundings, they act withdrawn and swim around hesitantly in the first few minutes. But curiosity soon prevails, and they begin to investigate their new tank. In contrast, the mutant fishes showed great difficulty becoming accustomed to their new situation, and they had a particularly strong reaction to being alone. They sank to the bottom of the tank and stayed completely still. The fish's behavior returned to normal when either of two drugs, diazepam, an anti-anxiety drug, or fluoxetine, an antidepressant, was added to the water. Social interactions, consisting of visual interaction with other zebrafishes through the aquarium wall, also helped alleviate depressive behavior in the mutant individuals. If fishes can be vulnerable to depression and anxiety, might they also take an active role in relieving it? Do fishes seek ways to chill out? A 2011 headline, "Calm down, dear, I'll rub your fins," described such a thing. Surmising that the caresses that reef fishes receive from cleaner fishes might heighten pleasure and relieve stress, a research team led by Marta Soares at the Higher Institute of Applied Psychology in Lisbon designed an experiment to test the idea. They caught 32 striated surgeonfishes from a region of Australia's Great Barrier Reef. Once they were Accustomed to captivity, the fishes were randomly assigned to either a stressed or non-stressed group. The unfortunate ones assigned to the stressed group were confined for 30 minutes in a bucket with water just deep enough to cover their bodies. This treatment had the intended effect of significantly raising their blood cortisol, a standard measure of stress. Then, stressed and unstressed fishes were individually placed for 2 one-hour sessions in a separate tank with a handmade, look-alike model of a cleaner fish. The shape and colors of the model closely mimicked a cleaner wrasse, a reef fish that makes a living by providing a cleaning service to customers such as surgeonfishes. In half of the tanks the model was stationary, in the other half, the model was mechanically rigged to move in a gentle sweeping motion. Stressed surgeonfishes were drawn to the mobile model like kids to candy. They swam over to the false cleaner fish and leaned their bodies right up against it. But they did this only if it was the one that could stroke them. They averaged 15 separate visits to the mobile model, compared to 0 visits to the stationary model. The strokes from the model also brought stress relief, as measured by cortisol levels that dropped when fishes had access to a moving cleaner fish model compared to stationary models. Cortisol also dropped in proportion to the time spent in contact with the moving models. With the characteristic reserve of a scientist, Marta Soares concluded, "We know that fish experience pain, maybe fish have pleasure, too." Despite the cutesy tone of the media report about fishes rubbing each other's fins, this is not science light. It unveils important implications about social living and having a quality of life. It supports the idea that pleasure motivates fishes to visit cleaner fishes, because the moving models were not removing parasites or anything else, yet the surgeonfishes still went to them repeatedly. Pleasure evolved to reward good behaviors that promote flourishing of the individual and perpetuation of its genes, hence, the good feelings we know that come from eating food, playing, staying comfortable, and having sex. Until recently, it was considered unscientific to even speculate on how fishes might be feeling emotionally. For this reason, most of the discussion has been restricted to the physiology of so-called reward systems. An elegantly simple scientific definition of a reward is anything for which an animal will work. In mammals, the dopamine system is a key player in the physiology of reward. When rats play, their brains release large amounts of dopamine and opiates, and when they are given drugs that block the receptors for these chemicals, they lose their attraction for sweet foods they normally enjoy. Fishes also have a dopamine system. If you give a goldfish a compound that stimulates the release of dopamine from his brain, such as amphetamine or apomorphine, the goldfish engages in rewarding behavior. He wants more of the compound. Goldfishes plied with amphetamine prefer to swim in a chamber treated with amphetamine, whereas goldfishes exposed to pentobarbital, a pleasure squasher, learn to avoid it. Amphetamine produces a rewarding effect in monkeys, rats, and humans, and this happens by increasing the availability of dopamine receptors in the central reward system. Since the goldfish brain has cells containing dopamine, the same mechanism is thought to be responsible for amphetamine's rewarding effects on goldfishes. Like some mammals, fishes are prone to abusing amphetamine and cocaine, unable to resist them when they are freely available. But in the case of those surgeonfishes sidling up to mobile cleaner fish models to get stroked, there is no addiction, just a fish responding to a desire for a pleasurable, therapeutic massage. Games fishes play. If you've won a prize, made a basket from the three-point zone, or seen a toddler squealing with delight while being playfully chased by a parent, then you know joy. One type of behavior that is joy-inducing is play. Play is useful, especially to young animals who need to develop physical strength and coordination, and to learn important survival and social skills. Play also has a psychological element. It is fun. Scientists have been exploring animal play for a good while. The German philosopher Karl Greuze published The Play of Animals in 1898. Animal play is not easily studied. It is a spontaneous activity, and the participants generally need to be feeling relaxed or happy to engage in it. Most observations of animal play are serendipitous. That is no barrier to Gordon M. Burghardt, an ethologist at the University of Tennessee with a striking physical resemblance to Charles Darwin. In a career spanning nearly 6 decades and hundreds of scientific papers, Burkhardt has not shied away from provocative topics, and that includes animal play where you might not expect to find it, or what he describes on his website as play behavior in non-playing taxa. In 2005, Burkhardt published the most comprehensive exploration of animal play to date. The cover of the Genesis of Animal Play features a tropical fish, a captive male white-spotted cichlid, pushing a submersible thermometer with his nose. Burkhardt and two colleagues, Vladimir Dinetz and James B. Murphy, have since published a study of 3 male white-spotted cichlids interacting with this thermometer, a 4.5-inch glass tube with a weight at the bottom, causing it to float vertically. Over the course of 12 sessions, the team recorded more than 1,400 instances of the thermometer being nudged with the 3 fishes, however placed individually in the tank for each session. Each fish had his own style. Fish 1 mainly attacked the top of the thermometer, causing it to wobble before returning to a vertical position. Fish 2 also liked to swirl around the thermometer, making contacts as he went. Fish 3 batted the object either from the bottom, the midsection, or the top. His hits were the most intense, causing the thermometer to bob about the tank and sometimes get stuck in a corner. Collisions between thermometer and the glass walls were loud enough to be heard from the adjoining room. Is it play? According to Burkhardt, it is play if 1. It does not achieve any clear survival purpose, such as mating, feeding, or fighting. 2. It is voluntary, spontaneous, or rewarding. 3. It differs from typical functional behaviors in form, target, or timing. 4. It is repeated but not neurotic, and 5. It takes place only in the absence of stressors, such as hunger, disease, crowding, or predation. The cichlid's behavior fit all of these criteria. White-spotted cichlids are not predatory, and the attacks they made on the thermometer did not resemble normal feeding behavior. The availability or absence of food had no consistent effect on their cavorting with the thermometer. The possibility of sexual behavior was sorely a doubt. The cichlid's interactions with the thermometer resembled their quick jabs at rivals, but were more repetitive, rather like a boxer practicing on a bag, and were engaged in only when the fishes were alone, unstressed, and perhaps understimulated. Given that the observation tank had other objects in it, including sticks, vegetation, and pebbles, why were these fishes especially attracted to the thermometer? The authors surmise that it might have been the reactive quality of an object that bounces back after being knocked, just like those old life-size inflatable clown toys weighted at the bottom to spring back upright whenever you hit them. Ethologists try to assume the animal's own perspective. Burkhardt interprets the bouncing back as a simulated counterattack by an opponent that was never successful. This is an example of object play. When two individuals interact playfully, biologists call it social play. Here's an example, courtesy of a former animal shelter worker based in Virginia. She had once shared a house with her husband, several cats, and a banded cichlid kept alone in a tank. The fish developed a sport with the cats, who would occasionally tiptoe over the bookshelves to drink from his aquarium. The territorial cichlid would lie in wait for the appearance of one of these furry invaders, hiding under the cover of some reeds in the corner of his tank. Experience had taught the cats to peer into the depths for any sign of an ambush, but the fish knew that and stayed quiet as a mouse. Only when the cat's tongue descended did he burst into action, propelling himself up through the reeds like a torpedo, hell-bent on taking a chunk out of that raspy organ. If she sensed the underwater eruption, the cat might get her first lap in before tongue and fish met. In time, the participants in this cat and fish game of wits showed signs that it was a welcome diversion from their quiet indoor lives. No blood was ever drawn on either side, but the cats would sometimes come right back, with a cocked head and sly eyes, to play the game again. That is not just social play, it is interspecies social play. A third variation on play is solitary play. In 2006, a German speech therapist named Alexander Reichel witnessed an example of solitary play during a visit to an art exhibition at the House of Art in Stuttgart. She describes the exhibit, titled Kunstlet, as a fantastic mixture with hidden treasures from all museums of the country. It included A large aquarium of about 130 cubic feet holding an exquisite collection of colorful and exotic fishes. As a fish lover, Alexandra spent a long time watching the goings-on behind the glass. She soon discovered a small, graceful, almond-shaped fish dressed in plush mauve with yellow and electric blue highlights. This one seemed to have a destination. She would swim in one direction along the bottom, then, on reaching the end of the tank, she swerved upward and swam to the surface. Arriving there, she was met by the current of a water pump, pushing the little traveler like a rocket back to the other side. There, she descended back to the bottom and started her circuit all over. Reichel shared with me, the funny thing is, I would call myself rather a pessimistic person, and the first thing I would think is that this is a stereotype due to the confinement. But this little fish actually seemed to have a lot of fun. I asked her why she thought it was fun. While most of the other fishes were just swimming about with no particular destination, this one looked so determined to have fun. I wanted to tell the others to follow her and enjoy her wild ride on the man-made current. It is not an isolated account. Burkhard has watched marine fishes in a very tall columnar aquarium repeatedly riding bubbles from an air stone at the bottom of the tank to the top. He thinks that this might be fun for the fishes, as it would be for us. Jumping for joy? If bubble riding is fun for a fish, might they also jump for joy? If you've spent any amount of time boating, fishing, or birdwatching at lakes and rivers, you have most likely seen fishes jumping out of the water. I have seen it many times. The law of averages dictates that it usually happens when I'm looking in another direction, and my eyes arrive at the action just in time to see a splash. Occasionally, I'm lucky enough to see the fish itself, and I've seen foot-long fishes and tiny inch-long ones leaping body lengths clear of the water. Certainly, fishes will exit water in desperate attempts to escape predators. Dolphins exploit the behavior, forming a circle and catching the panicked fishes in midair. But just as we may sprint from fun or from fear, different emotions might motivate fishes to jump. Mobula rays aren't motivated by fear when they hurl their large bodies skyward in leaps of up to 10 feet before splashing down with a loud slap. There are 10 recognized species of mobula rays, and their aerial stunts have earned them the nickname flying mobulas. They do it in schools of hundreds. Most of their leaps are calculated to land them on their bellies, but sometimes they do a forward somersault, landing on their backs. Males seem to be the initiators, so some speculate that there might be a courtship role. Other scientists think it might be a parasite removal strategy. Whatever its function, I posit that the rays are enjoying themselves. While kayaking in the crystal waters of Florida's Chisahowitzka National Wildlife Refuge, I watched several schools of 50 or more mullets moving in graceful formation. Mullets are as beautiful as they are common here. Their cream-colored tail margins and rear fins, and the yellow-tinged border between their metallic backs and white bellies were most evident when they leaped from the water, a behavior mullets are known for. Most of the time I saw 1 or 2 successive leaps by a fish, but one made a series of 7. Each jump was about a foot clear of the water and 2 to 3 feet in length. There are 80 species of mullets worldwide, and nobody knows for sure why they leap. They usually land on their sides, prompting theories that they are trying to displace skin parasites. Another idea is that they do it to inhale oxygen. The so-called aerial respiration hypothesis is supported by the fact that mullets leap more when the water is lower in oxygen, but is undermined by the likelihood that jumping costs more energy than is gained by gulping air. Might these fishes also be leaping for fun, a sort of fish play? Gordon M. Burkhard published accounts of a dozen types of fishes leaping and somersaulting repeatedly, sometimes over floating objects, sticks, reeds, sunning turtles, even a dead fish, for no clear reason other than entertainment. So far, nobody has subjected this intriguing possibility to scientific experiment. Maybe someone ought to catch a few smart fishes, put them in a lush tank with all the amenities. Then give them floating objects to jump over. Half a bathing suit. Let me share with you a little story of a feeling we all know well. It's the feeling we get when we pass an accident scene, are handed a wrapped gift, or overhear an argument in a restaurant. It's what we call curiosity. A scientist from Alaska told me about an encounter with curious fishes during a honeymoon swim at a vacant beach in Jamaica. She and her husband were snorkeling along a reef. An excellent swimmer, the husband discovered to his dismay that his bride was unable to dive below the surface. After his efforts to instruct her on how to dive failed, he tried a more drastic ploy. With considerable effort, he pulled half of my swimsuit off of me, then swam down and hooked it to a coral branch about 15 feet below. Surely I would have motivation to retrieve it, he told me with a laugh. Not a nudist by nature, I was quite upset even though we were apparently alone. I tried repeatedly to dive down to get it, but to no avail. All of this frantic activity had an unexpected effect on the local reef fishes. Rather than retreating, they began to gather around us. Then I noticed that Bob was also affected, in a very personal way. He swam over to me and made every effort to fulfill his manly urges. Alas, my own buoyancy prevented any successful conclusion to such efforts. We were amazed, however, at the reaction of the fish. Tiny little blue fish, angelfish, a rainbow of colors, shapes and sizes of reef life, formed a complete circle around us, Facingus, watching. Their bodies and tails quivered, causing them to look like a unified, shimmering mass. The husband finally took pity on her and retrieved the swimsuit. As the passion of the moment subsided, the fishes lost interest and the circle dispersed. That two humans who were making a fumbling attempt to perform an act that puts us all on the same plane were surrounded by shoals of attentive fishes continues to intrigue her. She still wonders what the fishes were thinking, and whether they were feeling the energy generated by the humans' amorous venture. Given fishes' sensitivity to sensory cues in their aqueous medium, several theories might explain what made voyeurs out of these fishes. As visually oriented creatures, our first inclination is to assume they were drawn to the young lovers' movements. But perhaps there was something about the electrical field or the body chemistry of the two humans that aroused their curiosity. Then again, maybe it wasn't benign curiosity the fishes were feeling, but unease as they monitored the intentions of a pair of potential predators. That, too, might bewet a curiosity, especially as these were not familiar intruders. When a fish takes notice of us, we enter the conscious world of another being. There is something exhilarating about that. For sure, studying fish emotions is a challenging scientific endeavor. But as we have seen, there are techniques to probe fish feelings, and the accumulating evidence indicates a range of emotions in at least some fishes, including fear, stress, playfulness, joy, and curiosity. Exploring how and what fishes think is less fraught with challenges than trying to study what they feel. As we'll see, the field of fish cognition has a lot to show for it. Part 4. What a fish thinks. Nothing is too wonderful to be true if it is consistent with the laws of nature. Michael Faraday. Fins, scales, and intelligence. Every other animal currently considered stupid and boring has its own amazing secrets. It's just that nobody has been able to discover them yet. Vladimir Dinet's Dragon Songs. Through time, evolution sees to it that animals become highly proficient at what is important to them. We cannot climb as well as a chimpanzee, who has 4 to 5 times our upper body strength. We cannot sprint like a cheetah, or hop like a kangaroo, and a speeding marlin would be at the finish line of a 100-meter race before Michael Phelps came up for his first breath. These animals need to move fast for survival more than we do, and natural selection dictates that faster individuals are more likely to carry their genes for fleetness into the next generation. The same principle applies to mental abilities. If nature presents a mental problem, and solving it confers a big advantage, then over time creatures may gain the capacity to perform cognitive feats we would otherwise think were beyond their grasp just because they are small, or not closely related to us. The modern scientific field of cognitive ecology recognizes that intelligence is shaped by the survival requirements that an animal must face during its everyday life. Thus, some birds can remember where they buried tens of thousands of nuts and seeds, which allows them to find them during the long winter months. A burrowing rodent can learn a complex underground maze with hundreds of tunnels in just 2 days. And a crocodile can have the presence of mind to carry sticks on her head and float them just below an area where herons are nesting, then pounce when an unwary bird swoops down to collect nesting material. If you didn't know a reptile could demonstrate planning and tool use, don't feel left out. Neither did scientists until this came to public attention in 2015. What about the mental abilities of fishes? Notwithstanding the liberties taken by filmmakers in popular movies like The Little Mermaid, Finding Nemo, and its sequel, Finding Dory, can fishes really think? Let's have a look at what fishes can do with those brains of theirs. Here's an example of fish intelligence, courtesy of the frillfin goby, a small fish of intertidal zones of both eastern and western Atlantic shores. When the tide goes out, frillfins like to stay near shore, nestled in warm, isolated tide pools where they may find lots of tasty tidbits. But tide pools are not always safe havens from danger. Predators such as octopuses or herons may come foraging, and it pays to make a hasty exit. But where is a little fish to go? Frillfin gobies deploy an improbable maneuver. They leap to a neighboring pool. How do they do it without ending up on the rocks, doomed to die in the sun? With prominent eyes, slightly puffy cheeks looking down on a pouting mouth, a rounded tail, and tan gray-brown blotchy markings along a 3-inch, torpedo-shaped body, the frillfin goby hardly looks like a candidate for the Animal Einstein Olympics. But its brain is an overachiever by any standard. For the little frillfin memorizes the topography of the intertidal zone, fixing in its mind the layout of depressions that will form future pools in the rocks at low tide, while swimming over them at high tide. This is an example of cognitive mapping. The use of cognitive maps is well known in human navigation and was long thought to be unique to us until discovered in rats in the late 1940s. It has since been documented in many types of animals. The goby's skill was demonstrated by the biologist Lester Aronson at the American Museum of Natural History in New York City. Around the time the rats were wowing us with their cognitive mapping skills, Aronson constructed an artificial reef in his laboratory. He compelled his gobies to jump by poking a predator-mimicking stick into one of his constructed tide pools. Fishes who had had the opportunity to swim over the room at high tide were able to leap to safety 97% of the time. Naive fishes who had no high tide experience worryingly successful at about chance level, 15% with just one high tide learning session. The little gobies still remembered their escape route 40 days later. It should be noted that these fishes were almost certainly stressed during these experiments, having been captured from their wild homes and confined in foreign surroundings. Indeed, several died of disease during Aronson's study, which suggests they were not thriving in their captive setting. In a recapitulation of patterns we see in other studies, individual performance reflected experience in their wild microhabitats. Fishes collected from beach areas that lacked tide pools at low tide did not perform as well as their seasoned comrades, though they still performed much better than chance. A recent study has found that the brains of rockpool-dwelling goby species are different from those of goby species that hide in the sand and don't need to jump to safety. The brains of the jumpers have more gray matter devoted to spatial memory, whereas the sand dwellers have a greater neural investment in visual processing. Frillfin gobies' ability to make mental maps, allowing them to leap accurately between tide pools, is a textbook example of having a well-honed mental skill wrought of necessity. As the biologist and author Vladimir Dinets, an authority on behavior and cognition in crocodilians, says, when people use the word intelligence, what they usually mean is being able to think the same way I do. It's a pretty self-centered way to view being smart. I suspect if a frillfin goby could formulate a definition of intelligence, it would include being able to form and remember mental maps. Remembering the escape route. Forming cognitive maps and recalling them weeks later illustrates more than a frillfin goby's prodigious talent for avoiding a leap of faith. It also exposes the human prejudice underestimate creatures that we didn't understand. I do not know what the species did to earn it, but the fish's legendary 3-second memory still lurks in popular culture. I still see an investment company's advertisement at airports that uses the goldfish's putative 3-second memory to contrast with the importance of our maintaining business connections. Being able to remember something is as useful to a fish as to a finch or a ferret. Tony Pitcher, a biology professor at the University of British Columbia, recalls a classroom study in an animal behavior course he taught many years ago. The students were exploring color vision in goldfishes. Each fish was assigned a feeding tube painted with subtly differing hues, and the fishes demonstrated their good color vision. After the study, the goldfishes were returned to an aquarium. The following year, some of these same fishes were combined with a new group of novice fishes for the study. When placed in the study habitat, the veterans quickly re-established themselves in their former tubes, making it immediately evident that each remembered the exact color and or location of its tube from 1 year before. The study of fish memories is not a new thing. In 1908, Jacob Reigard, a professor of zoology at the University of Michigan, published a study in which he fed dead sardines to predatory snapper fishes. Some of the sardines were dyed red, some not. The snappers didn't mind, and gobbled both types. But when Reigard made the red sardines unpalatable by the gruesome method of sewing stinging medusa tentacles into their mouths, the snappers soon stopped eating the red ones. Notably, the snappers still wouldn't touch red sardines 20 days later. This experiment not only demonstrates a snapper's memory but also his capacities to feel pain and to learn from it. My favorite study of fish memory comes from Cullen Brown, the biologist with a particular interest in fish cognition. Brown is the co-editor of Fish Cognition and Behavior, a book that has helped to propel the current revolution in our thinking about fish thinking. Brown collected adult crimson-spotted rainbow fishes from a creek in Queensland, Australia, and transported them to his lab. They are named for a kaleidoscope of bright colors arranged in bands of scales along their flanks. Adult rainbow fishes are about 2 inches long, and Brown guessed these ones were between 1 and 3 years old. He placed the fishes in 3 large tanks, about 40 to a tank, and allowed them a month to get used to their surroundings. On testing day, he removed 3 males and 2 females at random from their home tanks and put them in an experimental tank, equipped with a pulley system that allowed a vertical net to be pulled along the length of the tank. The mesh size of the trawl was less than half an inch, allowing the fishes a clear view to the other side without being able to squeeze through its holes. A single, slightly bigger hole measuring 3/4 of an inch across was placed at the trawl's center, providing an escape route when it was dragged from one end of the tank to the other. The fishes were given 15 minutes to adjust to their new environment, then the trawl was dragged from one end to the other over a period of 30 seconds, stopping just over an inch from the end. The trawl was then removed and placed back at its starting position. This constituted one run of the experiment. 4 more runs followed, at 2-minute intervals. 5 groups of 5 fishes were tested in 1997, then tested again in 1998. In the 1997 trials, the rainbow fishes panicked during the first run, darting about erratically, intending to cling near the tank edges, apparently not knowing what to do to escape the approaching trawl. Most of them ended up trapped between the glass and the net. Thereafter, their performance improved steadily, and by the 5th trial each shoal of 5 was escaping through the hole. When the same fishes were retested 11 months later, having not seen the experimental tank or the trawl in the intervening period, they showed much less panic than they had the previous year. And they found and used the escape hole on the first run at about the same rate as they had by the end of the 1997 runs. It was almost as if they had had no break and had 10 runs in a row. Brown told me. By the way, 11 months is nearly 1/3 of a rainbow fish's lifespan. That's a very long time to remember something that has happened to you only on one occasion. There are many other examples of fishes showing the remembrance of things long past. These include the studies showing hook shyness by carps for over a year, and paradise fishes who for several months avoided an area where they were attacked by a predator. And there are legions of anecdotes, like the story of Bentley, a captive humphead wrasse. When his usual dinner gong was reintroduced after months of disuse, Bentley raced to the spot where his favorite meal of squid and prawns was served. living and learning. Memory is closely intertwined with learning, for to remember something one must first come to know it. For almost every feat of learning displayed by a mammal or a bird, one can find a similar example in fishes, writes the fish biologist Stephen Reeves. If you want to impress someone with your knowledge of esoteric fish jargon, try rattling off these types of learning by fishes: non-associative learning, habituation, sensitization, pseudo-conditioning, classical conditioning, operant conditioning, avoidance learning, transfer of control, successive reversal learning, and interactive learning. You can watch YouTube videos of goldfishes being clicker trained to swim through hoops and push balls into miniature soccer goals. This is achieved through conditioning, or learning by association. On performing the desired behavior, the fish receives a stimulus, such as a flash of light, immediately followed by a food reward. The fish soon learns to associate both swimming through the hoop and the light flash with the reward. In time, the fish will know to swim through the hoop when it sees the light flash alone, and will hopefully perform the task even when no food is given. It's the same approach used to clicker-train dogs, cats, rabbits, rats, and mice. With some humility, we may recognize that the fishes are our captives, and we are the ones in control in experiments like these. Many are not given the enrichment and space they need, and instead spend their days in what often amounts to barren confinement, without the companionship of others of their kind, and with few if any places to hide. If the only way for an animal to get food is to push around a ball, he's likely to do it. If we were in a similar situation, we'd probably do it, too. On the other hand, this is still preferable to the common alternative of captive fishes getting no stimulation other than food and whatever activity they can observe going on outside the glass. Aquarium fish owners often report how their pets seem to know when it is feeding time. Simple captive experiments bear this out. For example, Cullum Brown and his colleagues fed captive Brachyraphis episcopi fishes at one end of their tank in the morning and the other end in the evening. Within about 2 weeks, the fishes were waiting at the appropriate place and time. Golden shiners and angelfishes take 3 to 4 weeks to achieve this so-called time-place learning. By comparison, rats take slightly less, about 19 days, and garden warblers learn slightly more complex tasks involving 4 locations and 4 time periods in just 11 days. These numbers are only modestly meaningful, for they assume equal levels of interest in food, the motivator used in learning experiments, over time. In fact, fishes normally eat at much slower rates than small birds, so it is harder to keep them motivated for learning experiments, and their learning rates may appear artificially slower. Fish's ability to learn quickly is being used to improve the poor survivorship of hatchery-reared fishes after they are released into the wild. Growing up in captive confinement, swimming in circles, receiving food pellets on schedule, and having no exposure to dangerous predators is a vastly different experience from surviving in the wild. Lacking the worldly survival skills of their wild compatriots, only about 5% of some 5 billion captive salmons released globally each year to build numbers for angling survive to full adulthood. Research shows that animals bred and reared in captivity for many generations can lose their ability to recognize predators, probably because the ability confers no survival benefit for them. But when the biologists Flavia Mesquita and Robert Young from Pontificia Catholic University of Minas Gerais, Brazil, exposed very young Nile tilapia to a taxidermied piranha, then immediately caught them at the bottom of the tank with an aquarium net, the tilapia quickly associated the unpleasant netting experience with the sight of the predator. After just 3 trials, tilapia were swimming quickly away in all directions. This scatter effect confuses predators. After 12 piranha netting experiences, the formerly naive youngsters had modified their anti-predator response by rising to the surface and remaining motionless. Control fishes who were not netted initially steered clear of the piranha model, a typical avoidance response by fishes toward a new, unfamiliar object, then soon just ignored it. When the trained fishes were retested 75 days after their last training session, more than half of them remembered what they had learned. Like most studies of fish cognition, these were performed on bony fishes. How do elasmobranchs score in learning tasks? As early as the 1960s, nurse sharks had Matched wits. With Mikey in. A black and white discrimination task, with both species performing at 80% success after 5 days. Damian Chapman with the Institute for Ocean Conservation Science has shown with playback experiments that oceanic white-tip sharks have learned to investigate fishing boats when they shut down their motors, because that signals that a fish has been hooked and there's an opportunity to get it before the fisherman does. These behaviors suggest a being with a mind. In a study of problem solving by a cartilaginous fish, a team of biologists from Israel, Austria, and the United States presented hard-to-reach food to vermiculate river stingrays, a freshwater species from South America. In the wild, these rays forage on small animals such as clams and worms buried in the sand by uncovering them and sucking them into their mouths. During training sessions, the 5 young stingrays soon learned that an 8-inch piece of plastic PVC pipe contained a piece of food, and they successfully accessed the morsel by creating water suction to draw it toward them. One of the 2 females was successful in all of her trials, perhaps because she appeared to watch the other rays before her first attempts. Within 2 days, all 5 rays had mastered the task. They used different strategies. The 2 females used undulating fin movements to create a current inside the pipe that moved the food toward them. The 3 males sometimes use this technique, but more often they use their disc-like body as a suction cup, or they combine the suction and undulation methods. Next, the experimenters upped the ante. They attached a black and a white connection piece to opposite ends of the pipe. The black connection piece had a mesh barrier inside that would block passage of a piece of food, while the white connection piece had no mesh. Each ray was tested over 8 sessions, and by the end all were successfully extracting the food from the pipe by working from the white end. Interestingly, all 5 rays changed their strategies during this phase of the study. The shift was generally from using undulating fin movements or suction to a combination of both. One male also blew jets of water from his mouth into the pipe to force the food out. These experiments show that stingrays not only learn, but that they can innovate to solve a problem. And they show tool use by using an agent to manipulate an object, in this case using water to retrieve food. Furthermore, moving away from a strongly attractive cue, the smell of food at one end of the tube, and trying the other side is not a trivial thing. It means they have to work against their natural impulse to follow chemical cues. That involves flexibility, cognition, and a sprinkle of determination. Malleable minds. You might be thinking that the 20% failure by mice and nurse sharks I mentioned a little earlier is still considerable, and that animals should perform at 100% if they want to be considered smart. But like other animals, fishes are not interested in their test scores. They don't succeed by robotically adhering to set patterns of living. They are evolved to be flexible and curious, to try new angles, to think outside the box. Even highly trained fishes will always explore alternatives. It's a productive way to behave in the real, dynamic world. With the ever-present threats of storms, earthquakes, floods, and, nowadays, human incursions, it pays to be light on one's fins. That said, I'm not even remotely suggesting that intelligence is uniformly distributed among the diversity of fishes. Inevitably, there are smarter and duller individuals. Then there are differences relating to a species' natural history. More challenging habitats demand more mental sharpness from their residents. As we saw in frillfin gobies living in different shore environments, variations in the sizes of different brain regions and in their associated intelligences can be found within a single species. Here's an example of how ecological challenges can affect intelligence, from K. Shinaja and K. John Thomas at Sacred Heart College, Kerala, India. In the wild, climbing perches occupy both still and moving water habitats. Individuals were collected from 2 Indian streams and compared for their ability to learn a maze with fishes collected from 2 nearby ponds. To navigate the maze, they had to find their way through a small door in each of 4 walls in their tank to get to a food reward at the other end. Guess who learned the route faster? It was the stream dwellers. They learned the maze in about 4 trials, compared to 6 trials for the average pond dweller. When the research team added visual landmarks by placing a small plant next to each door, the pond perches improved their performance to almost the level of the stream perches, who performed no better than they had before. Apparently, the pond dwellers found the landmarks useful, while the stream dwellers ignored them. Shinaja and Thomas have an elegant interpretation for these behavior patterns. Streams are more dynamic habitats than ponds because they are constantly subjected to the flow of water, including periodic floods. Stones, plants, and other landmarks are unreliable for learning a travel route because they are constantly changing as the water flows through. The most reliable constant is oneself. Thus, the better raw maze performance by the stream fishes may be attributed to their relying more on egocentric cues than visual ones. By contrast, landmarks are more reliable in a relatively stable habitat like a pond, so it pays to become familiar with them. Incidentally, studies that find population-level differences within a single species are interesting for another reason: they illustrate evolution in action. One can imagine that if these populations don't interbreed for many generations, they might eventually diverge to the extent that they are unable to successfully interbreed. That would qualify them as separate species. The malleable mind of a fish can be trained to correct unwanted behaviors, and that can be useful in captive situations. Lisa Davis, a zoological manager of behavioral husbandry for Disney animal programs, described to me how they corrected a behavioral problem they were having with their cobias. These large, sleek fishes grow to more than 6 feet and 172 pounds. With a gourmand's appetite, they are prone to becoming overweight in aquariums. The cobias under Davis's care were having this trouble as well. During feeding hours, they were outcompeting the other fishes. So Davis and her team taught them to swim to a particular station in their environment where they would be hand-fed pieces of food. This removed them from the competitive environment where other fishes were being fed buffet-style 20 feet away. The other fishes in the tank got their fair share, and the cobias returned to more normal weight. Win-win. Even their previously bulging eyes reduced back to normal positions, Davis told me. Similarly, when aquarium residents need medical attention, collaboration is best. Manta rays and groupers at Ocean Park, Hong Kong, the Georgia Aquarium in Atlanta, and Epcot Center in Orlando have all learned through positive reinforcement training to swim into stretchers for transport. Using positive reinforcement to train fishes to participate willingly in their care and feeding makes life more interesting and rewarding for captive fishes, and may help dispel former stereotypes about their intelligence. To this point, we've seen that fishes are not dunces, that they display features of having a mind and a mental life. But what about some of the more celebrated forms of intellect, such as the ability to plan and to use tools? Tools, plans, and monkey minds. Knowledge comes, but wisdom lingers. Alfred, Lord Tennyson. On July 12, 2009, while diving off the Pacific islands of Palau, Giacomo Bernardi witnessed something unusual and was lucky enough to capture it on film. An orange-dotted tuskfish uncovered a clam buried in the sand by blowing water at it, picked up the mollusk in his mouth, and carried it to a large rock 30 yards away. Then, using several rapid head flicks and well-timed releases, the fish eventually smashed open the clam against the rock. In the ensuing 20 minutes, the tuskfish ate 3 clams, using the same sequence of behaviors to open them. Bernardi, a professor of evolutionary biology at the University of California, Santa Cruz, is thought to be the first scientist to film a fish demonstrating tool use. By any measure, it is remarkable behavior from a fish. Tool use was long believed unique to humans, and it is only in the last decade that scientists have begun to appreciate the behavior beyond mammals and birds. Bernardi's video unveils new gems every time I watch it. I initially failed to notice that the enterprising tuskfish doesn't uncover the clam in a manner we might expect, by blowing jets of water from his mouth. He actually turns away from the target and snaps his gill cover shut, generating a pulse of water the same way that a book creates a puff of air when you close it fast. And it's more than tool use. By using a logical series of flexible behaviors separated in time and space, the tuskfish is a planner. This behavior brings to mind chimpanzees' use of twigs or grass stems to draw termites from their nests. Or Brazilian capuchin monkeys who use heavy stones to smash hard nuts against flat boulders that serve as anvils. Or crows who drop nuts onto busy intersections and then swoop down during a red light to retrieve the fragments that the car wheels have cracked open for them. Like a seaborne celebrity, the tuskfish draws an aquatic audience. Fishes of several types swim up to watch the sand blowing in action, and others briefly join our hero during his swim to the rock, like reporters hoping for a good quote. Halfway to his destination, our tuskfish stops to try out a smaller rock lying on the sand. He makes a couple of half-hearted whacks, then heads on his way again, as if he's decided this one's not worth his time. Who can't relate to his misguided attempts and how they reflect the fallibility of a mortal life? These are impressive cognitive feats for any animal. That they are performed by a fish clearly upsets the still commonly held assumption that fishes are at the dim end of the animal intelligence spectrum. Even if this particular tuskfish were a rare Stephen Hawking among fishes, his behavior would be remarkable. But what Bernardi saw that day was not exceptional. Scientists have noticed similar behavior in green wrasses, also called blackspot tuskfishes, on Australia's Great Barrier Reef, in yellowhead wrasses off the coast of Florida, and in a 6-bar wrasse in an aquarium setting. In the case of the 6-bar wrasse, the captive fish was given pellets that were too large to swallow and too hard to break into pieces. Using only his jaws, the fish carried one of the pellets to a rock in the aquarium tank and smashed it, much as the tuskfish did the clam. The zoologist who observed this, Lucas Pascoe from the University of Wrocław in Poland, saw the wrasse perform the pellet-smashing behavior on 15 occasions, and it was only following many weeks of captivity that he had first noticed it. He described the behavior as remarkably consistent and nearly always successful. Hard-nosed skeptics might point out that this sort of thing isn't real tool use because the fishes aren't wielding one object to manipulate another, as we do with an axe splitting a log for firewood, or a chimpanzee does by using a stick to get to the tastiest termites. Pascoe himself refers to the wrasse's actions as tool-like. But this is not to demean the behavior, for as he points out, smashing a clam or a pellet with a separate tool is simply not an option for a fish. For one thing, a fish isn't equipped with grasping limbs. In addition, the viscosity and density of water makes it difficult to generate sufficient momentum with an isolated tool. And clasping a tool in his mouth, the fish's only other practical option, is inefficient because fragments of food would float away, only to be snatched up by other hungry swimmers. Just as the tuskfish uses water as a force for moving sand, the archerfish also uses water as a force, only this time as a hunting projectile. These 4-inch-long tropical marksmen, sporting a row of handsome black patches down their silvery sides, mostly inhabit brackish waters of estuaries, mangroves, and streams from India to the Philippines, Australia, and Polynesia. Their eyes are sufficiently wide, large, and mobile to allow binocular vision. They also have an impressive underbite, which they use to create a gun barrel of sorts. By pressing their tongue against a groove in the upper jaw and suddenly compressing the throat and mouth, archerfishes can squirt a sharp jet of water up to 10 feet through the air, with an accuracy in some individuals of nearly 100% at a distance of 3 feet. Woe betide a beetle or a grasshopper perched on a leaf above the backwaters where these fishes lurk. The behavior is notably flexible. An archerfish can squirt water in a single shot or in a machine gun, like fusillade. Targets have included insects, spiders, an infant lizard, bits of raw meat, scientific models of typical prey, and even observers. Eyes, along with their lit cigarettes. Archerfishes also load their weapons according to the size of their prey, using more water for larger, heavier targets. Experienced archers may aim just below their prey on a vertical surface to knock it straight down into the water instead of farther away on land. Using water as a projectile is only one of many foraging options for these fishes. Most of the time they forage underwater as ordinary fishes do. And if a meal is within just a foot of the surface of the water, they may take the more direct route, leaping to snatch it in their mouths. Archerfishes live in groups, and they have fantastic observational learning skill. Their hunting prowess doesn't come pre-installed, so novices can only make successful shots at speedy targets after a prolonged training period. Researchers studying captive archerfishes at the University of Erlangen-Nuremberg, Germany, found that inexperienced individuals were not able to successfully hit a target even if it was moving as slowly as a half-inch per second. But after watching 1,000 attempts by another archerfish to hit a moving target, the novices were able to make successful shots at rapidly moving targets. The scientists concluded that archerfishes can assume the viewpoint of another archerfish to learn a difficult skill from a distance. Biologists call this perspective taking. What an archerfish does might not require the same level of cognition as that shown by a captive chimp who carried a disabled starling up a tree to help launch it back to the air, but it is nevertheless a form of grasping something from the perspective of another. High-speed video recordings reveal that these fishes use different shooting strategies depending on the speed and location of flying prey. When using what the researchers call the predictive leading strategy, archerfishes adjust the trajectory of their sharp jets of water to account for the speed of a flying insect. They aim farther ahead of the target if it is moving faster. If the target is flying low, archerfishes often use a different strategy, which the researchers term turn and shoot. This involves the fish firing while simultaneously rotating his body horizontally to match the lateral movement of the target, causing the jet of water to track the target on its airborne path. These fishes would do any quarterback proud. Archerfishes compensate for the optical distortion produced by the water-to-air transition, and they do this by learning the physical laws governing apparent target size and the fish's relative position to the target. Having a generalizable rule of fin like this enables an archerfish to gauge the absolute sizes of objects from unfamiliar angles and distances. I wonder if archerfishes also practice entomology, visually identifying insects in order to know whether they are tasty, whether they're too big to eat or too small to bother with, or whether they sting. Most likely, archerfishes have been squirting water jets for at least as long as humans have been throwing stones, and I suspect that wrasses were using rocks to crack clams open long before our ancestors started bashing hot metal against anvils in the Iron Age. But can fishes spontaneously invent tool use, as we can when unexpected conditions require us to improvise? In May 2014, a study highlighted an example of innovative tool use by Atlantic cods being held in captivity for aquaculture research. Each fish wore a colored plastic tag affixed to the back near the dorsal fin, which allowed the researchers to identify them individually. The holding tank had a self-feeder activated by a string with a loop at the end, and the fishes soon learned that they could release a morsel of food by swimming up to the loop, grabbing it in their mouth, and pulling on it. Apparently by accident, some of the cods discovered that they could activate the feeder by hooking the loop onto their tag and then swimming a short distance away. These clever cods honed their technique through hundreds of tests, and it became a finely tuned series of goal-directed, coordinated movements. It also demonstrated true refinement, because the innovators were able to grab the pellet a fraction of a second faster than by using their mouth to get the food. That fishes are routinely expected to interact with a foreign device to feed themselves is impressive enough, but that some devised a new way of using their tags shows a fish's capacity for flexibility and originality. Tool use by fishes, so far as we know, seems confined to a limited number of fish groups. Cullum Brown suggests that wrasses in particular may be the fish's answer to the primates among mammals and the corvids among birds in having a greater than expected number of examples of tool use. It could just be that living underwater offers fewer opportunities for tool use than living on land. But we do know that the tuskfishes and archerfishes are prime examples of evolution's boundless capacity for creative problem solving, and they might turn out to have plenty of company among other fishes. Might we count tigerfishes among them, turning the tables? For millennia, birds have been diving into the water to catch fishes. Pelicans, ospreys, gannets, terns, and kingfishers are among the more spectacular examples of an army of feathered fish foes. Gannets, who measure over 3 feet long and can weigh 8 pounds, launch themselves downward from a height of 50 to 100 feet and can be going 60 miles per hour when they fold back their wings just before impact and torpedo to depths of 60 feet to grab an unsuspecting fish with their pointed beaks. Sometimes the tables are turned. In January 2014 at Schroeder Dam, a man-made lake in Limpopo Province, South Africa, scientists documented on film something that locals had reported seeing before. As a trio of barn swallows skimmed just above the water, a tigerfish leaped up and snatched one of the birds out of midair. Tigerfish are serioval-shaped, silver-scaled predatory fishes of African freshwaters. There are several species, the largest of which can reach 150 pounds. They are named for horizontal stripes along their sides, and for the rows of large, sharp teeth that line their mouths. They are prized by fishermen as a game species. The swallow capture wasn't an isolated incident. The research team that published it reported about 20 separate swallow snatching incidents per day, which represents as many as 300 barn swallows meeting their maker during the 15-day survey. Think about that for a moment. Swallows are known for their speed and agility as they maneuver after insects on the wing. These birds are probably going at least 20 miles per hour when they suddenly become fish food. I have a hard time imagining a fish without any presence of mind having any success at catching a swallow in flight. Without planning, I think a million hopeful random fish leaps and snaps at the air wouldn't yield a feather. Even if the tigerfish waited just below the surface for an approaching bird, then launched straight up from the depths, as great white sharks do to catch seals porpoising across the surface, I am guessing said fish would be doing an air snap at a swallow long gone. But the grainy footage of a successful catch didn't reveal a vertical leap by the fish. Instead, the bird was ambushed from the rear. In the video of the fish catching the swallow, the fish leaps at great speed from directly behind the bird and overtakes it in midair before splashing back into the water. The four ecologists described two distinct methods of attack being used by the tigerfishes. One involves skimming along the surface immediately behind the swallow, then launching to catch it. The other is a direct upward attack initiated from at least 1.5 feet below the surface. The advantage of the first approach is that the fish need make no adjustment for the surface image due to light refraction at the water surface, which from underwater makes the swallow appear to be behind where it actually is. One disadvantage of this method is that it may compromise the element of surprise. Obviously, at least some of these fishes have learned to compensate for the distortion angle of the water surface, or else they would have no success with the second method. This behavior raises a host of questions. How long have tigerfishes been doing this? How did it originate? How was it transmitted through the tigerfish population? And why aren't swallows taking evasive action to avoid being caught, such as flying farther above the water? I decided to ask the lead author of the Tigerfish Bird Predation Studies, Gordon O'Brien, a freshwater ecologist from the University of KwaZulu-Natal School of Life Sciences, in Pietermaritzburg, South Africa. The tigerfish population in Schroeder Dam was only established very recently from the lower reaches of the Limpopo River in around the late 1990s. So the population there is very young, replied O'Brien. Although tigerfish are faring well within most of their range, in South Africa they are declining due to numerous human impacts. As a result, tigerfish have been placed on the South African Protected Species List, and introductions to man-made habitats are ongoing. I asked O'Brien how the bird hunting behavior originated. He explained that from a tigerfish's perspective the dam is very small, and that he believes the population has been forced to adapt or perish. He and his colleagues saw many larger individuals in very poor condition around the period when this behavior was first recorded in 2009. O'Brien also had quite a bit to say about the ways in which bird hunting is transmitted through to jerfish populations. This seems to be a learned behavior. Smaller individuals are not as successful and prefer a surface chase approach to ambushing and striking from deeper below the surface, where the individual has to compensate for the light refraction. We know that a jerfish are very opportunistic and are attracted to heightened activity of other individuals. They get into some sort of a feeding frenzy. When the swallows return on their migrations, the sight is quite spectacular, and I think that it is during this period that the younger learn the behavior. Aviary is not unique to tigerfishes. Largemouth bases, pikes, and other predatory fishes have been witnessed on rare occasions leaping up to grab small birds perched on reeds near the surface. Large catfishes were recently filmed catching pigeons who come to drink from the shallows of the River Tarn in southern France. They use the same ambush technique used by orcas to catch sea lions, lunging and beaching themselves temporarily as they try to grab the prey with their mouths. It isn't likely that these fishes are showing off. They may actually be hunting birds out of desperation. Schroeder Dam is a man-made habitat built in 1993, and the tigerfishes were introduced there to help boost their populations, which were dwindling elsewhere in South Africa. Earlier study had shown that the Schroeder Dam tigerfishes are spending considerably more time foraging than other local tigerfishes, possibly due to food scarcity in the lake. The behavior may even put the tigerfishes themselves at risk of predation from African fish eagles, who are common in the area. The pigeon-catching catfishes at the River Tarn might share a parallel plight. Introduced in 1983, they have survived, but pigeons are not normally on a catfish's grocery list, and the fishes may be pursuing the birds due to a documented shortage of their usual prey, smaller fishes and crayfish. If necessity really is the mother of invention, then it applies to fishes, too. The authors of the discovery at Schroeder Dam site published notes from 1945 and again in 1960 from other locations in South Africa by biologists who suspected that tigerfishes were catching birds in flight. Maybe one enterprising tigerfish made a lucky strike at an unsuspecting swallow, then honed his or her skill through practice. The behavior could have spread through the population by observational learning, which fishes can be very good at, as archerfishes demonstrate. However it has the hallmarks of flexible, cognitive behavior. It is opportunistic, since it is unusual behavior for the species. It requires practice to develop, and skill to execute. It is most certainly transmitted through observational learning. And different methods are used. As for why the swallows have not learned to avoid tigerfishes by flying higher above the water, there are several possibilities. The swallows simply aren't aware they're being caught by fishes. The birds benefit energetically by flying just above the surface, and that's where most of the insects are. It seems doubtful that the birds haven't detected the danger, for it would be hard not to notice a sizable fish bursting from the water to grab a colleague flying nearby. Maybe capture by a fish is too rare an event, and the benefits of foraging near the surface too great, for the swallows to abandon surface flying. Fishes versus primates. If fishes can innovate and learn to perform exacting, risky maneuvers to catch food, can they also reason their way through a space-time puzzle designed by humans? Imagine you are hungry and I offer you 2 identical pieces of pizza. I also tell you that the one on the left will be removed in 2 minutes, while the other one will not be taken away. Which piece will you eat first? Assuming you're hungry enough to eat both pieces, you will almost certainly start with the piece on the left. Now imagine you are a fish, a cleaner wrasse, in this instance, and you are offered a similar situation, 2 plates of identical food that differ only in their color. If you start eating from the blue plate, then the red plate is removed. If you choose red first, the blue plate is left where it is and you can have both. Since we can't simply tell a fish that the red plate will be removed first, the fish has to learn it by experience. Elsewhere, similar experiments have been done with 3 species of brainy primates, 8 capuchin monkeys, 4 orangutans, and 4 chimpanzees. Who do you think did better? If you guessed it was one of the apes, no pizza for you. The fishes solved the problem better than any of the primates. Of the 6 adult cleaner wrasses tested, all 6 learned to eat from the red plate first. It took them an average of 45 trials to figure it out. In contrast, only 2 of the chimpanzees solved the problem in less than 100 trials. The remaining 2 chimps, and all of the orangutans and monkeys, failed the test. The test was then revised to help the primates learn, and all of the capuchins and 3 of the orangs got it within 100 trials. The other 2 chimps never did. The researchers, 10 scientists in Germany, Switzerland, and the United States, then presented the successful subjects with reversal tests, in which the plates suddenly took on the opposite roles. No one took well to this bit of deviousness. And only the adult cleaner wrasses and the capuchin monkeys switched preferences within the first 100 trials. Several juvenile cleaner wrasses were also tested, and they performed markedly worse than the adult fishes, indicating that this is a mental skill that must be learned. One of the study authors, Redouin Cherry, even tried the test on his 4-year-old daughter. He set up an equivalent foraging trial, placing chocolate mandams on distinctive permanent and temporary plates. After 100 trials, she had not learned to eat from the temporary plate first. The authors draw a key conclusion: the sophisticated foraging decisions which cleaner races demonstrate are not easily achieved by other species with larger and more complexly organized brains. But these skills did not come out of the blue. The race's shrewd choice of which plate to eat from first resembles decisions these cleaner fishes have to make in the wild during interactions with client reef fish. And the logic of the experiment was deliberately designed to mimic that situation. Brain size be damned, if it's critical to a species' survival, then that species will most likely be good at it. Because cleaner fishes make their living by gleaning tidbits from the bodies of other fishes who have their own agendas, they need to be more attentive to the possibility that that food source might swim away at any moment. Bananas don't do this, transient client fishes do. And cleaners get a lot of practice. Even on a slow day at the office, cleaner races service hundreds of clients. When business is booming, they can have more than 2,000 interactions per day with a great variety of clients, some of them regulars who are residents of the reef, others visitors who are just passing through. Cleaners are able to discriminate between the two, and they start by servicing visiting clients who will swim off and visit another cleaner at another station if not inspected immediately. Regulars will still be around later on. Red plate, blue plate. If you're like me, you're rather disappointed in the performance of the primates in what to us seems like a fairly straightforward mental challenge. The apes' unexpected lack of success appeared to be due to frustration with the task, write the authors. It certainly isn't because they are stupid. Great apes are renowned for solving puzzles, some of which they do better than humans can. For instance, chimpanzees far outperform humans in a spatial memory task with numbers randomly scattered on a computer screen. They also have the wits to use Archimedes' principle, which exploits an object's buoyancy when confronted with a peanut sitting at the bottom of a clear narrow tube. Unable to dislodge the peanut or to reach into the tube, they will retrieve water from a nearby source, carry it in their mouths, and squirt it into the tube until the peanut floats within reach. Some inventive chimps will even urinate into the tube. Orangutans make mental maps of the locations of hundreds of fruiting trees in their forests, as well as the schedules on which they produce fruit. They are also renowned for their escape artistry, being able to pick locks, and they have even tricked keepers into giving up their keys. But those are different types of skills. It also probably didn't help the primates that they were all born in captivity, where food was routinely provided several times per day and was not taken away. By contrast, the races were wild-caught and had to fend for themselves during their lives. When fishes outperform primates on a mental task, it is another reminder of how brain size, body size, presence of fur or scales, and evolutionary proximity to humans are wobbly criteria for gauging intelligence. They also illustrate the plurality and contextuality of intelligence, the fact that it is not one general property but rather a suite of abilities that may be expressed along different axes. One of the reasons that the concept of multiple intelligences is so appealing is that it helps explain how one person can be an excellent artist or an accomplished athlete yet do rather poorly at, say, mathematical or logical tasks. It diminishes the importance we have historically placed on intelligence as defined by a selection of human abilities that's too narrow even for our own species. To this point, most of what we have explored has involved fishes acting as individuals. But few fishes live alone, most are social creatures, and their societies reveal new facets of their lives. Part 5. Who a fish knows. Friendship isn't about whom you have known the longest. It's about who came and never left your side. Anonymous. Suspended together. We of alien looks or words must stick together. C. J. Sansom. Take a cursory glance at fishes swimming around a coral reef, and you might think they are just a higgledy-piggledy assemblage of creatures. Take a closer look and you'll notice structure in who they choose to swim with. During my travels around the world as an ethologist, I've been able to watch fishes in a variety of settings, both captive and wild. From Florida to Washington, D.C., to Mexico, I've seen the different ways fishes aggregate and move about. Snorkeling at Biscayne Bay and off Key Largo in southern Florida, I encountered many dozens of fish species. Some, such as the stingray who swam away from me in the shallows of a beach, and a barracuda who hung motionless over a reef, were alone. Most, however, swam with others of their kind. Atlantic needlefishes parked themselves near shore in small groups just beneath the surface. French grunts drifted in compact clusters, swaying with the undulating currents. A band of 18 midnight parrotfishes ambled casually along the bottom, making audible crunching sounds as they gnawed on coral rocks. Yellowtail snappers were less gregarious, but I never saw one alone. Although mixed species shoals are common, fishes clearly recognize members of their own kind and generally favor their company. The who swims with who effect is muted in captive aquaria where there are fewer representatives of each kind. On a visit to the Smithsonian Institution's National Museum of Natural History in Washington, D.C., I lingered in front of a live coral reef display. The tank contained about 20 fish species and a smattering of invertebrates, prawns, sea urchins, sea stars, and anemones. A pair of yellowtangs, solid lemon-yellow fishes shaped like a disc with a pointy mouth, the species represented by Bubbles in Finding Nemo, rarely strayed more than 2 inches apart. A duo of damselfishes took turns making repeated dashes to the surface to gulp air before doubling back in an instant. A second damselfish pair swam calmly nearby, staying within inches of each other, each mirroring the other's movements. There were also 2 sets of clownfishes, a pair who nestled among the filaments of an anemone near the bottom of the tank, and a trio who swam near the surface. I was watching an organized community of autonomous beings with social lives. Even though captive fishes have no say in who they are stuck with, I admire that they still manage to form harmonious relationships. Aquariums illustrate what science demonstrates: fishes have social lives. They swim together, they recognize other individuals by sight, smell, voice, and other sensory channels, they choose mates non-randomly, and they cooperate. The fundamental social unit for fishes is the shoal or school. A shoal is a group of fishes who have gathered together in an interactive, social way. Shoaling fishes are aware of each other's presence, and they seek to remain in the group, but they swim independently, and individual fishes may be facing in different directions at any given time. A school of fishes is a more disciplined form of shoaling, in which fishes swim in a more orderly fashion, each going the same speed and in the same direction and each spaced a fairly constant distance from the next. A shoal of fishes is likely to be foraging, like the midnight parrotfishes I mentioned earlier, whereas a school is more likely to be in transit. 1 million sardines migrating along the Adriatic coast are schooling. Schools tend to be larger and longer lasting than shoals. While snorkeling with my girlfriend off the west coast of Puerto Rico in April 2015, we experienced a large school of fishes, probably scaled herrings, up close. Gazing at the lovely reef colors a few feet below us, we suddenly found ourselves in a cloud of small, silvery gray fishes migrating northward along the shore. Each fish was about the size and shape of a metal nail file, and each swam about 3 inches from the others. Their large eyes bore a slightly worried look, and the doggedness of their swimming, propelled by the constant, rapid flickering of their tails, gave an impression of earnestness. Underwater visibility was poorer than usual due to windy weather, and such was the number and density of this school that nothing else was visible beyond them. We were enshrouded in fishes. I turned and swam with them for a few seconds, and felt the eerie sensation of being in motion yet not moving relative to my surroundings. They seemed completely unperturbed by the presence of these two knobby, bumbling apes in their midst. I caught glimpses of silver flashes to my seaward side, the flanks of larger fishes ambushing them from the depths. A minute passed and the little migrants were gone as abruptly as they appeared, continuing on their northward journey. Why do fishes form large schools like this? Benefits of schooling and shoaling include ease of movement, predator detection, information sharing, and strength and safety in numbers. Many fishes moving in the same direction produce a current, so school members save energy just as a peloton of cyclists cuts wind resistance. There is some evidence that slime shed from the bodies of migrating fishes reduces drag. Studies of schooling Atlantic spadefishes indicate that this effect might increase swimming efficiency by 60%. A subsequent study of wild-caught captive Atlantic silversides has thrown some doubt on the drag-reducing hypothesis. When researchers added a synthetic drag reducer to a flow tank in quantities far exceeding the amount of mucus that would be sloughed off a school of 10,000 silversides in natural conditions, they saw no relative decline in tail beat rates by the fishes swimming in the tank. In a large school of migrating fishes, schoolmates are surely anonymous, but fish shoals contain familiar shoalmates, and research finds that familiar shoals behave more efficiently than shoals of unfamiliar individuals. Familiar shoals of fathead minnows show tighter cohesion, more dashing behavior, and less freezing. Familiar shoals perform more predator inspections, in which 1 or 2 shoal members approach a nearby predatory fish essentially to serve notice that the predator has been spotted and is not likely to make a successful surprise attack. Even when you're surrounded by colleagues, some positions in a school or shoal are better than others. In experiments at the University of Cambridge, the fish biologist Jens Krauss saw no tendency for chubs to position themselves with a shoal of 20 individuals when the shoal was undisturbed. But when Krauss introduced the fish alarm substance Schreckstoff into the water, the chubs suddenly showed a strong preference for swimming near others of their own size. Bigger chubs swam near the center of the shoal, and smaller ones were relegated to the less protected periphery where predators are more likely to strike. Krauss could detect no signs of aggression, but somehow the fishes knew their place. Position in the shoal is not the only anti-predator tactic used by groups of fishes. Just being in a group is likely to reduce predation risk due to the confusion effect. Predatory perches, pikes, and silversides, for example, have lower success in picking off prey fishes from larger schools. It is uncertain how the confusion takes place, but one biologist likens the baffled predator to a child in a candy shop who is so overwhelmed by all the choices that she cannot decide which candy to get. The visual homogeneity of single-species shoals enhances the confusion effect. In a shoal of minnows, individuals marked with India ink are at higher risk of attack from a pike. No wonder black or white mollies presented with a choice of shoaling with either black or white fishes choose shoalmates who match their own color. Avoiding conspicuousness may be another reason that fishes prefer to shoal with non-parasitized fishes than with shoals afflicted by many parasites. Beyond the benefit of sheer numbers, there are more active ways in which the collective actions of a large number of fishes reduces the vulnerability of any one member of the group to capture by an enemy. Fleeing schools will perform the fountain effect, splitting into 2 clusters that quickly swim around each side of a predator fish and reassemble behind it. If the predator turns around, the maneuver is repeated. The fountain effect exploits the fact that while the predator fish is faster, the prey are more agile, and they can better avoid a predator who is facing away from them. The behavior requires the same sort of rapid attunement to others that can be seen in vast flocks of birds that appear to change direction in an instant. A spectacular variant of the fountain effect is the flash expansion, in which all the fishes in a school dart away from the center as the predator attacks. The spray of fishes may cover 10 to 20 body lengths in just 1/50th of a second. Despite the speed of this movement, the prey fishes never collide, leading to speculation that they must somehow know which direction they and others are planning to go before they dart away. Studies with the banded killifish show that they form different size groups depending on context. Theories developed by behavioral ecologists predict that larger schools are a better defense against predators, while smaller shoals are better for foraging due to lower competition. That probably explains why killifishes presented with food and alarm cues together formed larger groups than when presented with food only, but smaller groups than in the presence of alarm cues alone. Who's who among fishes? Under our superficial gaze, individual fishes in a single species school can appear so alike that we may rightly wonder if they can tell each other apart. Not only can they do so, but Redouan Sherry, a leader in fish behavioral research from the University of Neuchâtel, Switzerland, is not aware of any study of fish society where researchers failed to find individual recognition. Fish's suite of well-developed senses may act individually or in combination for recognizing other individuals and distinguishing one's own kind from other species. In captivity, European minnows, for instance, can be trained to recognize other fish species by smell alone, even though they probably rely on additional cues in the wild. As we know, fishes also can recognize individuals of species other than their own, such as participants in cleaner-client relationships. Cullum Brown has studied individual recognition in fishes. He was curious to know whether it mattered to a fish whose company it was put in. It did matter. In about 10 to 12 days, guppies became familiar with new guppies in their midst, and they could learn to recognize at least 15 fellow guppies. Why would this be useful? One reason is that, like wolves, chickens, and chimpanzees, guppies establish social hierarchies, and knowing one's position in society is useful. A smart guppy can know when to take advantage of his higher rank over a lesser shoalmate, and when to avoid punishment for insubordination by higher-ranking individuals. Furthermore, guppies may use this knowledge from a third-party perspective. They are more likely to behave aggressively toward the loser of a fight that they have witnessed between two other guppies. At the same time, the fighting males know who is watching them, or at least they know what sex the audience is. If the audience is female, they curb their aggression, presumably because females do not like to mate with aggressive males. But if the witness is a third male, they make no effort to restrain themselves. Dominance hierarchies require individual recognition, and these audience effects infer awareness of relative ranks. For example, the East African freshwater cichlid fish Astatilapia bertoni has been shown in experiments to infer that if fish A is higher ranking than fish B, and fish B is higher ranking than fish C, then fish A must be higher ranking than fish C. There are other ways of exploiting knowledge of who's who among fishes. Experiments with European minnows show that they recognize and prefer to associate with shoalmates who are poorer competitors for food. Individual fishes plucked from groups that had been foraging together preferentially spent time on the side of a tank with less efficient foragers than on the side with more efficient foragers. Bluegill sunfishes, and probably many other fishes, make the same kind of discriminations. A fish recognizing another fish is one thing. But can a fish recognize you? As countless aquarium enthusiasts will attest, fishes can and do learn the identities of the humans who care for them. One example came to me from Rosamond Cook, an ecologist with the Biological Monitoring Program in Riverside, California. While doing a postdoc at Colorado State University from 1996 to 1999, I worked in the Fishery and Wildlife Biology department. Students had set up a freshwater tank in a hallway near my office, and it held a young smallmouth bass. When the students left for the summer, there was nobody left to feed the fish, and I volunteered to help. After a few weeks, I noticed that the bass would swim eagerly to the glass and up to the surface whenever I approached. I thought perhaps he recognized me. I mentioned this to one of the fishery professors, who assured me that fishes do not recognize individual people. When fall arrived and the hallways filled with students, I continued to observe the behavior of the bass. I sometimes watched him secretly from down the hall, and I never saw him respond to the presence of others. But any time I came near the tank, he came out to greet me, even when I was 10 feet away and surrounded by other people. I cannot explain this fish's behavior other than that he recognized me and could pick me out of a crowd. Cook told me she later released the bass in a large pond on property owned by the university where no fishing is allowed. In April 2014, I struck up a conversation with a former U.S. Fish and Wildlife Service employee who was netting some minnows in a backwater of the Potomac River and collecting them in a bucket of water. The little fishes were destined for a home aquarium where he has kept a largemouth bass for years. I sometimes feed him feeder goldfish from PetSmart, he said, but this is cheaper. Given what I had learned from Rosamond Cook and countless other fish watchers, I asked him if he thought the bass recognized him as an individual. Absolutely. I'm the one who feeds him, and if my wife or daughter are in the room, he doesn't stir. But if I enter, he swims to the nearest corner of his tank and wags his tail like a puppy dog. Does science back up a fish's purported ability to recognize a human? Yes, according to a study of archerfishes. When presented with two human faces, the archers quickly learned to select the one that was accompanied by a food reward. Border Patrol. Being able to recognize other individuals is useful in maintaining and defending your particular spot of surf and turf. Territoriality is widespread among fishes, which use a number of techniques to say shove off, to trespassers, spreading fins and gill covers to look bigger, swimming in place with exaggerated movements, making popping noises with the mouth, changing colors, chasing, and, usually as a last resort, biting. One of the best lectures I've ever attended was delivered years ago at a meeting of the Animal Behavior Society. The topic was like a just so story plucked from a Rudyard Kipling collection. Renee Goddard's study of hooded warblers changed the way I thought about the mind of a tiny bird. Weighing less than half an ounce, hooded warblers have superb navigation skills. Those who survived their annual migration between the eastern United States and Central America returned to the same little patch of forest they occupied the previous year. There the colorful little sprites re-established their residences through song and active border patrol. Remarkably, Goddard discovered that male hooded warblers recognize their familiar neighbors from year to year. By playing back the individual songs of these neighbors, she found that the occupant birds tolerated neighboring males' calls as long as these emanated from the particular males. Known territory locations. However, if she moved the loudspeaker and broadcast the same calls from the other side of the occupant's territory, the occupant freaked out. It's as if your next-door neighbor unexpectedly greeted you from the house across the street. Recognizing an individual's song after an 8-month hiatus, but associating it with a particular location, is quite remarkable for such a tiny creature. And you might be wondering what it has to do with fishes. Enter the three-spot damselfish. Damselfishes comprise about 250 species of small, colorful fishes found in tropical waters of both the Atlantic and Indo-Pacific Oceans. They include the clownfishes made famous in Finding Nemo. Despite their demure name, damselfishes are renowned for their fearlessness in defending their spot on a reef. Many times while reef diving in Puerto Rico, I saw yellowtailed damselfishes tearing out of their alcoves to chase away larger fishes who strayed too close. So, can a three-spot damselfish recognize his neighbor as Goddard's hooded warblers can? Years before Goddard studied warblers, Ronald Thresher was conducting studies to address this question. Thresher was at that time a postdoctoral student in marine science at the University of Miami, and he chose to work with three-spot damselfishes living on reefs off the coast of Panama. He came up with a simple and effective method to compare the reaction of territorial three-spot damselfishes to simulated intrusions by other three-spot damselfishes. First, he identified territory holders. Then he caught neighbor damselfishes who shared a territory boundary with the occupant, and stranger damselfishes whose home turf lay at least 50 feet away. Next, he placed the neighbor in a transparent gallon bottle and the stranger in another bottle. Finally, holding a bottle in each hand and starting from the territory of the neighbor fish, he slowly moved the two bottles toward the occupant's territory. Thresher conducted at least 15 sets of presentations to different damselfish males, noting the point at which the territory holder began to attack, and whether he attacked the two unwitting intruders differently. He also presented pairs of two different species to the occupant 3 spots, a closely related dusky damselfish from the same genus, and a less related species, the blue tang surgeonfish. The response to bottled strangers and bottled neighbors was strikingly different. Territory holders vigorously attacked the strangers, ramming the bottle and trying to bite them through the confounding barrier. In contrast, they virtually ignored the neighbor fish in the adjacent bottle. When presented with pairs of the other damselfish species, or pairs of surgeonfishes, residents did not discriminate between the two. Companion experiments by Thresher determined that these damselfishes were recognizing their neighbors by size and especially by the subtle differences in their color patterns. All fishes were a thoughtfuler turned to their own territories, where hopefully they were able to re-establish their well-earned places on the reef. Nobody has since tested whether damselfishes can remember their neighbors after a long absence the way hooded warblers can. Perhaps they don't need to, since they are not a migratory species. But I wouldn't be surprised. Like damselfishes, some bumphead parrotfish males are also territorial. Named for their bulbous, bony foreheads, these reef giants grow to 5 feet and 165 pounds. During territorial disputes, a pair of males swim at each other from a distance of several yards, and their foreheads make a loud crunch when they collide. The behavior resembles the head-butting displays of bighorn sheep, and it serves a similar purpose. Two males square off and butt heads repeatedly until one of the pair balks and swims away. Although they involve violence and are certainly not risk-free, these ritualized contests generally avert serious injury or death, thereby allowing the victor to retain his turf and the vanquished to venture off to greener pastures. Battle-scarred veterans may sport dents in their bumps, which become white through scales and away. Surprisingly, it was not until 2012 that headbutting by bumphead parrotfishes, or for that matter any marine fish, was recorded. Scientists conjecture that a reason for our failure to notice the behavior might be that it is becoming less common. As bumpheads become scarcer due to overfishing, there may be fewer competitors to do battle against. Personality is not just for persons. Individual recognition and competitive contests hint at another dimension to be found in societies: personality. Personality is well established in land animals. What about fishes? Some years ago, I ordered takeout from an Asian restaurant in my neighborhood. As I waited for the food, I took to loitering near the entrance, where there was an aquarium housing 3 Garibaldis. Garibaldis are bright red fishes native to the Pacific Ocean, about 8 inches long, and named after Giuseppe Garibaldi, an Italian military and political figure whose followers often wore a characteristic scarlet or red shirt. The 3 fishes' permanent home at the restaurant, which featured a faux rocky outcrop, a couple of plastic plants, and a bed of colored stones, was barren and monotonous compared to their native reef habitats, where they can live to 15 years. As I watched them over several separate visits, 3 random red fishes resolved into 3 discrete individuals, a social unit with patterns of behavior. One of the 2 slightly larger fishes was always separate. I only ever saw him on one side of the aquarium, away from the rocks at the other end where the other 2 generally swam, about 3 feet away. I saw postures and interactions that looked submissive, assertive, and affectionate. Once, the loner and one of the pair sparred near the midline, each making brief lunges at the other. There were nudges and nips, but nothing blatantly violent. On another occasion, one of the pair swam on its side near the bottom while the other made gentle pokes at its body with the mouth. In the wild, male Garibaldis clear a nest site for their mates. More than once, I saw a cone-shaped depression in the blue gravel that lined the bottom of the aquarium, so I think these fishes were feeling the urge to nest. Male Garibaldis are strongly territorial and will sometimes nip at divers who enter their nesting area. I'm guessing this trio was a mated pair and an extra male. Perhaps the outlier would have done better to become a female. Garibaldis are among many species of fishes that can switch gender at various times during their life cycle. In total, I spent barely 30 minutes watching these three fishes, which represented a tiny fraction of the mural of their lives. But in that time, I witnessed something that stayed with me. I realized I was watching not just three random fishes, but three individuals with autonomous, independent lives. They were there for about 4 years, then one day I returned to the restaurant to find them gone, replaced by several smaller fishes of different species. Those three Garibaldis, for all intents and purposes, were individuals with personalities. It seems to be so with all fishes, whether a humble herring, a sea bream in a Chinese food aquarium, or a reef shark named Grandma. To hear Christina Zenato talk about Grandma Yuknosh describing someone she cares about, with a personality, she has a soft nature, and a way of approaching me with the desire to be petted and touched. She is usually very keen to come to me. Even when somebody else is down there with food and I am some distance away, she will approach me before anybody else. Sometimes when I let her go, she quickly turns and comes back into my lap. Grandma is an elderly Caribbean reef shark and the favorite of Zenato, an ocean explorer, conservationist, and certified dive instructor. Athletic, ebullient, and fearless, Zenato has spent 20 years diving with sharks at her home base in the Bahamas and around the world. She also hyper-relaxes them with gentle stroking, then removes hooks from their mouths. For Zenato, a shark is a someone, not a something, an individual with preferences, attitudes, and persona. Christina named Grandma for her pale color, which she likens to the gray hair of an old lady. They have known each other for 5 years. Grandma's the biggest of the group of Caribbean reef sharks that regularly visit one of Christina's diving spots. Based on her size, 8 feet from nose to tail, Grandma is about 20 years old. Zenato's affection for this shark appears to be mutual. She is rather gentle. She loves to come close to me and allow me to pet her. As mutual trust grows, the bonds I create with these sharks are spectacular. Grandma disappeared for a week in early 2014. Zenato had noticed that Grandma was pregnant and guessed she had gone to find a secluded place to give birth. Slow to reproduce, Caribbean reef sharks produce a litter of just 5 or 6 live-born babies every 2 years. As the days passed and Grandma still hadn't shown up, Zenato grew worried. Another week went by, and then she was back, noticeably sleeker, having delivered her babies into the ocean's cradle. She swam faster. She was wanting food following the labor of birth. I could see it in her body language, her posture. Their reunion brought sheer happiness. Being around sharks so long has taught Zenato their independent nature. There is a relationship with sharks that teaches us the true meaning of no strings attached, no expectations. And it makes the relationship different from our human expectations, but also more beautiful. I care deeply about Grandma. When I see her, I smile, and she brings me joy. She seems to enjoy our relationship, too. Zenato is no less enamored of the bony fishes she encounters and sometimes feeds on her dives. In one area where she dives often, she has befriended 3 black groupers, Peanut, the Whisperer, and Secret Agent. She describes them as extremely intelligent, curious, and attuned to her thoughts. How does she tell them apart? It is no harder than distinguishing your math teacher from your mother. Their colors, shapes, body features, and behaviors vary from one to the other. At nearly 5 feet, Peanut, whose olive gray body is cloaked with black blotches and brassy spots, is the largest of the 3. A bite sustained when she tried to steal a piece of fish dangling from a shark's mouth left her with a disability that prevents her from changing the color of the right side of her face, so when her body turns pale to signify a relaxed mood, the right side retains a black mask. It's a fish's rendition of the Phantom of the Opera. The other 2 groupers in this trio are also distinctive in their appearance, with Secret Agent being next in size and the Whisperer the smallest. Zenotto considers Secret Agent the prettiest. Her skin is pristine, unblemished with marks or discolorations, and she has a more slender face. But even if the groupers were identical in size and coloration, they would be as different as pie from cake. In spite of her handicap, Peanut is the extrovert among the grouper trio. As soon as she sees Christina with food, she swims straight up to her face. Peanut has learned Christina's signals for not your turn to eat and your turn to eat. Even without food, she will approach me and nudge my hand to be stroked, says Zenotto with a smile. She loves the feeling of my chainmail diving suit over her skin. Secret Agent is named for her habit of keeping just outside Zenotto's field of vision, hovering behind and below just to the right or left side of her back. Like Peanut, Secret Agent has learned the difference between shark feeding time and grouper feeding time. The Whisperer is the shyest of the three. She is always hovering behind Zenotto's ears, as if whispering to her, "Drop me a fish, drop me a fish." But like a feral cat, the Whisperer remains distant, never allowing Christina to touch her. If I turn or move, she turns and moves with me, always staying out of sight unless I jerk my head fast around and catch her by surprise. Creatures like Grandma and the Whisperer defy the common prejudice that sharks are terrorists and bony fishes primitive and dull. Natural selection acts on variation across individuals, and for complex creatures with minds and social lives, personality is an expression of that variation. You don't have to have fur or feathers to have personality, scales and fins will suffice. Fish bonding. Because fishes don't have expressive faces, we tend to find them difficult to identify with or feel for. Consider, though, that dolphins also cannot change their facial expressions, but we do not harbor the same prejudices against them. Perhaps this is because their expression looks happy, or because we know them to be big-brained mammals. Or both. Yet, there are solid evolutionary bases for the formation of close bonds among fishes, for such roles as mating, parenting, cooperation, and security. And there are numerous personal accounts that attest to social connections that go beyond mere acquaintance. Sabrina Galmassian kept fishes while doing graduate studies in English in New Mexico. She was naive about aquariums and didn't think fishes had much going on upstairs when she acquired a 1-inch-long gold barb. Frankie lived alone in an aquarium with a snail and a frog. He would often poke at these tank mates, but didn't get much reaction and seemed bored. So Sabrina purchased a second gold barb. She named her Zoe. Frankie's behavior changed immediately with the new arrival. His body vibrated with apparent excitement when Zoe was introduced, sending ripples through the water. As Galmassian describes it, he had an instant and natural love for the new tank mate. It was surprising, considering that he had lived alone for so long. I have since had other fish who are afraid or uninterested in tank mates. But this was love at first sight. Zoe was at first rather uninterested in Frankie. In time, she warmed to him, and the two barbs began a companionship.